experiment. So that will be on the level we experimentalists can understand property of this dopants. So I'll start with transition metal ions, and then at the end I'll say why we are interested in the rare earth ions and what we are doing and what we can understand and where is the progress and new things. So let me go page down, page up, nothing happens. How I don't know why.
Try left, right.
Nothing working. Should I try once more? I'll try once more. I'll start and restart it for some reason.
Olku, włącz mikrofon, bo cię nie słychać. A Marku, chyba dobrze jest udostępniać ekran, a nie prezentację.
Okay, okay. Thank you.
Udostępniać ekran. I thought that I was doing it.
Na dole masz taki, and try move forward.
Nothing is happening for some reason. And now I try this way. And what happened now? Wow, it's works.
Yes, it works.
I have my microphone on, so I don't know why I was claiming that. I think
No, Oleg has a microphone switched off, and he tries to say something. So
okay.
It was Oleg. Sorry.
Okay,
Sorry.
so I will start with transition metal ions, and historically, the first model, which was used for many years, was proposed by Ludwig Woodbury. And it was proposed to describe what we see in electron spin resonance. And my career in the institute started, as Oleg said, many years ago, 50 years, started with, and I was working my PhD using electron spin resonance. So that's why I made this model using. And model was very simple, that we have d orbitals, like 5 of them. From quantum mechanics, we know how they look like. 3 of them are T2 orbitals, 2 E orbitals. And as long as possible, we should put 1 electron with this same alignment of spin on each of these orbitals. If we'll try to put second electron, it costs a lot of energy. They interact each other, repulse. So we have exchange splitting. And this for ion in vacuum is very simple. The only parameter what we should introduce is just exchange splitting, and that's it. But if we put transition metal ions to crystals, and I would just say situation in compounds with high symmetry, so it can be either tetrahedral or octahedral system, then we should look for d orbitals and how the density of electrons is directed towards ligands or not. And this was a basis of how they describe the ions. And they say that we have large exchange splitting and much smaller crystal field splitting. So this case is called high spin approximation. Now we know that there's some cases that this approximation is not working, but I'll continue with this idea of high spin approximation. And then they say that if we exclude things like Jahn-Teller, which can be observed, and chromium was one of the canonical case of Jahn-Teller effect, static Jahn-Teller effect, spin orbit, spin splitting. In fact, we need only to know 2 parameters. exchange splitting value and crystal film splitting, and then we'll analyze what happens in material. And that's if we, for example, have TD symmetry, then for electrons on E orbitals, the density is not looking towards ligand. So then the repulsion will be smaller. For T2, the electron density, they look towards the ligand. So we have electron-electron interaction. And this is the origin of crystal field splitting. So the model will be like this shown here. I don't know if you could see my mouse. They will have E to T splitting, and this is parameter delta, which says what's the strength of crystal field splitting. And exchange splitting is much larger. So that's very simple situation. And if we change to octahedrals, we just reverse, then it costs more energy to have electron on E orbitals and less on T2 because they are not looking towards ligands. So the splitting will be like here, that we have T2, E, and this is exchange splitting, which was assumed to be much larger. So, for example, if we go to case, for example, like chromium ion, and which was discussed to describe what we see in electron spin resonance, then 2 electrons are given to bonds, and then we should analyze how many carrier electrons we have. For chromium 2+, we have 4 electrons, and we just look for the splittings, and we can calculate, if we know the rules of quantum mechanics, what will be the energy terms. And what we should know, it's called by Hund's rule that the ground state has the largest multiplicity. Multiplicity is 2 times spin, total spin plus 1. And among the states with the same multiplicity, we'll look for the ones with larger orbital number, and that will be the ground state. So the rules are simple. So we can easily calculate full energy structures. And for each ion, and the Hund's rule says that if we know for D1 configuration, immediately we know for D9 and so on. So this is the situation we can calculate just based on rules and splittings described by this very simple crystal field effect. So when the Ludwig Woodbury proposed their models, they say, okay, we put transition metal ions, and the only things what happens is what I described. If they come to 2,6 material in place of cation, 2 electrons are given to form the bonds, and the rest is just exactly described in the way I explained. And the model was quite successful because it correctly said what we see in electron spin resonance. It said the spin multiplicity. Also, the ground state was correctly described. And the problems only started, and that was first indication that something is missing when we look for splittings and higher energy terms. Something was wrong. And that was the first indication that the model proposed was too simple. And a real problem came when 3,5 materials were studied. And when chromium in gallium arsenide was studied, suddenly people observed that we have 3 charge states within the band gap. And it was quite unexpected because band gap of gallium arsenide is 1.5 electron volt. And for 3 ions, it costs about 20 electron volts to ionize the center. So how it's possible that within the 1.5 electron volt, we suddenly have 3 charge states of this impurity. Also, the splittings and energy states could not be described using only 2 parameters of crystal field model. And what was also quite surprising when people look for selection rules for transition. Either for intrashell transition, DT, or for case if we have photoionization, if we have 2, 3 charged states allowed, then we can look for what are the intensities for valence band to impurity compared to impurity to conduction band transition. First should be parity allowed, PD transition, and second, DS should be parity forbidden. So formally, people expect a large difference in intensity of this transition, whereas they observe practically the same intensity, and that was quite surprising. So the model I will show, the schemes I've done are very intuitive. Do not look for how I took the splitting between S and T2 states of ligand. This is just very schematic. So how to understand what happens? So let us concentrate on chromium. That was the case when it was clearly shown that the model breaks down, and it's not easy to explain what we see. So if we have chromium, chromium is very special case because electron configuration of chromium, 0, I mean, not ionized ions, is 3d54s1. This is one of this multi-electron system where this rules know for one electron and order how we put them on different shells breaks down. So 3d5 4s1. So on the right side, I prepare such situation that we have 5 electrons on the lowest E and T2 states. I took the situation for tetrahedral environment, and then still 1 electron we put somewhere on above, on something which has like symmetry of S state. Ligand, we have 6 electrons, 2 of them are on S states, 4 on T2, and for simplicity, I do not put only 1 level here, and I put one of us electron spins should be on opposite directions that the 3 others here. And now what we should include are the rules of quantum mechanics, and the things I'm speaking is due to von Neumann. Von Neumann was in fact father of computer. And this is so-called anti-crossing rule, that if we have states of the same symmetry, they cannot cross and they should repulse each other. So what happened now if I put chromium to the crystal and just forming the bonds? Now, states of the same symmetry should interact. So this S state should interact with S states here from chromium, so it should be pushed a little down. E states are not affected, but T2 states are affected because they interact, and that one is pushed down a little compared to the situation it was for atom in a vacuum, and this upper is hooked up. And this also is here affected. And what we see now, that something which many, many years intuitively was proposed by Sławek-Biernacki, he proposed that if we want to describe correctly the situation and energy terms, we should assume that we have like 2 crystal field splittings and 2 exchange splitting. Suddenly are in line what we observe, and we include so-called the name of what happens was called strong polarization model of hybridization, but it's not important. Important is to take into account and take into account rules we know from quantum mechanics. So if we look for this, and then we ask a question, why the Ludwig Woodbury model works so well through many years and people do not question it? We can calculate what is the total spin, what we are getting. In fact, it's exactly what's predicted by Ludwig Woodbury model. But splittings are quite different. And moreover, this interaction between the T2 states of ligand and a transition metal atom means that we have hybridization. So no longer we have pure D-like states. And it means that the rules we say that valence band, transition metal ions, transition metal ions, conduction band in case we have photoionization transition should be characterized by quite different selection. It's no longer true because we never have pure D-like function now. They always are mixed with P function of ligand. And P.A.S transition is parity allowed. So, okay, total spill is okay. And this is in line with first used for many years based on this Ludwig Woodbury model. But now we see that what was then used, and I remember still works of our late colleague Sławomir Biernacki, who was using this idea, 2 values for exchange and 2 values for crystal field splitting, are well explained by model I showed. And that's also important that suddenly we could explain why the selection rules now are not leading to very weak DD transition, because they're never really parity forbidden transition. We always have some admixture of P states, so that's okay. But let's now try to, can we explain this enigma I mentioned, why this photoionization transition are so much energy for this transition, so much reduced compared to the situation we had for ion dopant in vacuum. So the model I'm showing is prepared that way that we start once more with this very schematic model, and they said, okay, the one here, okay, my mouse is now showing it. We can say that is something, I can say core states, and these are these external states. And now I'll try to...
Marek, could you say who introduced this model?
This model, at first was Anderson, but then we usually collect with Peter Vogel and Jacek.
In fact, this model was, as you said, by Anderson and Haldane, 2 Nobel Prize winners.
Yes. And then it was, for us, it was very much connected because Peter Vogel was often coming to Poland. So he was one of the person using it. Our colleague who worked with Peter Vogel, Jacek, he was also using it. So that's are the names I should mention, yeah. So what will happen now if we check how will the model will change if we add 1 electron? So I'll go towards from chromium to a plus to 1+. So to prepare it, I put 1 extra electron on ligand. So this level here should do the electron-electron interaction and go up. If this level goes up, this level here will be less affected and also will shift slightly up. And I put some arrows in here, how it will affect position of different ones. What is important for us, then now suddenly if we look for what has in core area for core states, we'll see now that this shift of the level T2 symmetry up means that like density of electrons in the core region is some way reduced. And if it's reduced, it's possible, and it was very interesting to calculate, is that like if we say we add 1 electron, but in sense of what happened in core states, it's like we add only fraction of electron. And it means the energy normally used for ions in the atoms in vacuum, which was pretty large, now is very much reduced, and it can be reduced even in chromium. In gallium arsenide, it was reduced 50 times, so it's quite a large effect. So, okay, now if we go from chromium plus to chromium 3+, then it means that we just remove 1 electron from T2 shells. Instead of 6, we'll have like 5, just to explain it. And this means that due to reduced electron repulsion, this level will go down. If it's go down, it'll push these two levels by interaction also down. It means that density of electrons in core area is increased. And it's not reduced by 1, but it's reduced by fraction of 1. Now, a lot of people said that this model should also be used to explain what happens if we have some donors in materials and acceptors. So this kind of a charge neutrality model was then used to also analyze not only the case of transition metals, but also some general problem, how to describe the effects that we add or take one electron for some system, and how will it affect the density of electrons in core region. Now, I'm working now on rare science, and if I show this kind of a picture, we immediately see that situation must be very different. Because what is happen, this rare science are 4Fn systems. So we have up to 14 electrons of F shell, but F shell is always inner shell. So all effects like we discussed for transition metal ions, that D shell is some way external, are here much, much weaker. So crystal field splitting will be much weaker. And also, this idea put forward that how we can explain the effects ionization, so that it's no longer working. So where is the problem? Maybe not problem, where are the advantages? This hybridization model, which was intuitively proposed by transition metal, is not working. So it means that we'll have like atomic-like spectra. So we expected that emission and excitation spectra for emission are more or less like for atoms, and they are very weakly dependent on host, environment, splitting, and so on. But disadvantages, yes, but for some of application, and this area will work through last few years using these dopants to use as kind of a labels. This seems quite good because very sharp emission, very sharp excitation spectra. That is characteristic feature of rare science. Size-independent emission, for if we put them to some particles, perfect. But we have a problem because emissions should be very weak. Whereas of transition metal, we should say that all the selection rules are not really working because we always have like a mixture of ligands piece wave function to D. Here, it should not be terms. So the 4F emission should not be efficient. These are really parity forbidden processes. But in some cases, we see that we can quite intensively excite this emission, and we can use it. And this started a lot of studies to use rare science for different applications, also in practical devices. So what I'm showing here, for example, the things we are studying, we use this fact that this is so characteristic sharp emission, and so we introduce small nanoparticles to blood circulation, and they can enter that are affected by pathological changes. We studied here, these are results for case of lung cancers, and we can use this emission, and this emission is bright enough to distinguish from emission from cells, so-called autofluorescence. But practically, the things we started to work and look for explanation why this emission can be bright in some cases was with John, and this is cooperation we started many years ago with a group from Finland, where they work on so-called thin film electroluminescent devices. So this TFEL is thin film electroluminescent. And the idea was first based on observation coming from many, many years before, and it was coming from previous Soviet Union, that if we take such phosphor, zinc sulfide with manganese, if we bombard these phosphors with electrons, we can observe relatively bright yellow-orange emission, actually, and that's what's observed. And then people propose that we can use this fact in practical device. So we have phosphor, and this is zinc sulfide with manganese. It's embedded between two layers of insulating materials, can be, for example, aluminum oxide. Then we applied voltage. If these layers are thin, relative voltage size can be pretty high, like megavolts per centimeter. And then from some interface states, we can excite, inject electrons to phosphor, and they gain energy so fast that you can say they are ballistic. And the mechanism proposed was just they excite emission of manganese to plus by just impact excitation. So then we could observe a pretty bright emission, and that led to first devices. And actually, a first system was built like this. So this year, phosphor, it was zinc sulfide, manganese, two thin films of dielectric materials, metal electrodes on bottom, top. Voltage was applied. It was enough to apply like few volts. Taking into account these layers were pretty thin, like say 1 micrometer. Field inside was pretty high, so these electrons could easily excite emission of transition metallites. So first practical device was built. There's some problems to be solved, like time stability of such devices, and actually atomic layer deposition was introduced to produce such devices. And that's very important because this is technology interest from the first day to produce devices, and Bennick company still produce such devices. They're pretty good, but they're too expensive to use them in laptops. But for some applications, they are used and they're pretty good. And if somebody traveled to Helsinki previously, it was possible to observe the largest display in the world using this kind of the system. And it works through many, many years without any failure. So it showed that it's quite interesting. But then people ask, okay, yellow color is one, but we want to make multicolor. And this pushed people to work to look how to get various colors. And this is the moment we joined this research. I mean here myself, Krzysztof Świątek, Andrzej Suchocki. So we start cooperation with group from Helsinki, and our role was to advise what kind of a matrix to use and what the dopants. And immediately we turned our idea that we should try rare science. And especially attractive was europium, which we studied, and we looked at europium in some of sulfides, can be 2 charge states, 3+, 2+, ionization. And we start to see what should be the matrix to get it. Actually, it's a so-called this reference model used first and introduced by Alex Zunger for transition metal ions, worked beautifully in case of rare science, and we could predict matrices and so on. So why we convince our colleagues from Helsinki that they should use other matrix than zinc sulfide? They should go to strontium sulfide. And the reason was that if we go to strontium sulfide, after this excitation to make like from 2+, 3+ europium, mechanism was quite efficient because now we replace impact excitation by impact ionization, and It means the cross-section for the process was a few orders on magnitude larger. But then we can expect the retrapping of electron to form 2+, but this retrapping can occur, if it will be possible, by upper D-like state of europium. And DF transition is parity for allowed and should be quite efficient. But zinc sulfide was too smaller band gap. So if we go to calcium sulfide, strontium sulfide, it should be okay. And actually, when we proposed this to our colleagues from Finland and done it, and they got very nice and efficient emissions. So that was indication that rare earth can be interesting. So actually, this is our report. And we say that we can have this mechanism, and we can predict where this level and what kind of energy we need. To calculate it, we also use so-called Yergensen model to get to this kind of two zigzag curve you can see here. So it was pretty good prediction and actually led to practical results. We also said that another very interesting impurity in the sense can be not only europium, but for example, praseodymium in strontium sulfide. So it opens the long list of possible matrices and candidates to bright emission, and we studied it, and together with Professor Niisto and Marko Leskala from Technical University of Helsinki and Marko Leskala from University of Helsinki, both work in chemistry departments. We propose materials to be used and what can be the mechanism responsible for this efficient citation. And this landed a large review, which I wrote then with Marko Leskala about the processes. But in this review, I already added some new possibilities, and I wish now to discuss it. So once we start to study emission in different matrices, we often observe that in addition, if we our detection for this line of europium, and then we look for PLE, so photoluminescent excitation, we see some channels due to like higher terms, but then often we observe very strong and broad bands related to energies close, very usually close to expected band gap of different materials. And we start to look what can be the origin of this efficient excitation mechanism. If it's like FD, or maybe it's something to do with like host excitation. And we could see this kind of a bonds in many of systems. So this was for europium, ion, zirconium dioxide, and praseodymium. And quite often they say natural way in many publications was to say that this is 4N, 4F, 5D excitation. This is a loud process and can result in quite efficient energy paths. But then we could see that something happens on this high energy wing here, which looks more or less like host excitation. And that was discussed what can be the origin. And in addition to this kind of what I put in circles, like excitation to higher like terms related to F electrons, also something which looks like host excitation. And I'm once more showing that if we go to matrix we use now in our bio experiments, we look for matrices and mechanisms to get good fluorescent labels to detect cancer cells. We also see something like this. And we can see that we see quite broad and intensive bands looking that there are aerobic effects like band-to-band excitation. So the model which was first discussed by many people say that, okay, we have like band-to-band process. Electrons are trapped by donors, pulled by acceptors. So maybe we can have kind of the energy transfer from donor-acceptor pair to rarest ions. And this will explain why we need band-to-band excitation. And if we do it, close pairs will decay quite efficiently. For distance pairs, chances for energy transfer are increased, and this will explain how we can pump energy to rarest ions, and that's maybe the mechanism responsible. So the very detailed study were done looking if this mechanism really works for zinc sulfide. And the idea is that, okay, now let us directly excite the donor-acceptor pairs, and let us look if we have now the same bands appearing in a PLE, photoluminescent excitation band, for different rarest ions. And they show a P because what I'm showing is just a ladder of different excited state for different rarest ions. This is a place we excite directly. It's a so-called green or blue emission of zinc sulfide. And if energy transfer is efficient, we should have this place for this rarest ions. And actually, the answer was no, we do not observe it. So this mechanism cannot be efficient. Maybe it may appear, but it's not efficient. It's not the way to explain what we see. Then this was the work I've done during the visit in a group of Rob Amerland, cooperating with our colleagues, unfortunately late Tom Gregorkiewicz. And then I continued this work done at Adrian Kozanecki. We noticed that for some of the 3,5 ions, like terbium, we see something strange. So we excite band to band. We have different emissions. Some of emissions are relating to donor acceptor pairs, bound excitons. And now what we start, we apply the methods of heating carriers. And for this, we use so-called optically detected cycle resonance. And we look what will happen with different emission. We start to increase the free energy of carriers, like electrons. And suddenly we start to see that the effect is just reverse we expected if the energy transfer is efficient. So if intensity of donor accepted pair bands are reduced or band excited bands is reduced, efficiency of terbium emission under this host excitation is increasing. And that indicates the mechanism we speak must be different. And what was proposed, and this was something this problem I discussed with this big reviewers, Marco Leskala, looking through many direct, indirect reports for both transition metal ions and rarest ions. Then the mechanism we can consider is that if we have like transition metal ions or rarest ions, such center can bound electron hole pair. So it will be something like bound exciton, and it can pass energy very efficiently, rarest ions, and this will explain why we can have so efficient pumping of energy and then recombination if we have band-to-band excitation. So actually, how it's possible? And then if we look for something which was a study and many years, and the person who first put forward the idea what can be origin of the strange lines was Paul Dean. It's also called satellites of band excitons. It was observed that in addition to main excitonic recombination line, sometimes on low energy side, we have plenty of very sharp lines and satellites. And they were not explained through quite long time until this idea of Paul Dean came and co-workers. Then it can be due that excitons decays And part of energy is transferred for excitation of impurity bounding excitant. So it can be donor, it can be acceptor. And I would like to turn your attention to one point. Then what we see here, that we can see very efficient 1s, 2s excitation, 1s, 3s, 1s, 4s, and so on, until in some cases even 8s line is observed. But if we want to make absorption experiments, this kind of transitional S-line are forbidden, parity forbidden, very strictly. So we do not see, we see 1s, 2p, and so on. And it was said, okay, that if we have like 3 carriers bound on one centers, then all the symmetry looks like broken. Rotational symmetry in the system of 3 carriers means that then we have broken selection rules, and we can expect quite efficient transition, which normally are difficult to observe. That was quite interesting concept for us, because it means that if we have such case that rare ion bounds exciton, then in fact energy can be quite efficiently pumped to the system. The obvious question is it possible? And then I looked for model which is due to Hopfield's Thomas Lynch, HTL, which was proposed to describe something which in physics we incorrectly say isoelectronic bound exciton center. It should be isovalent centers bound exciton. So for example, if we put nitrogen plus phosphorus in 3 5s, number of valence electrons is the same. And then why we should call isovalent system. But still, we can have the situation, then we have strain billet because radiuses can be different. These two may have different electronegativity, and this may lead to bonding of carriers. So let's assume that we have situation like for nitrogen in gallium phosphide place of phosphorus, then due to very strong electronegative nitrogen, electron can be trapped by short range potential. Center is charged, immediately long range Coulombic potential is formed, which I schematically show like this. And then hole will be trapped quite efficiently. Or we can have a reverse situation. The hole will be first trapped for other centers, then electron will attract by long-range Coulombic potential. So for such center, it was proposed that difference in electronegativity and strain, local strain field, are responsible for what happens. And this means that if we look, for example, like a local strain, and then for like this case, canonical case, like nitrogen in place phosphorus, gallium phosphide, people in fact observe whole family of this, because if we put somewhere nitrogen, it affects the lattice. So sometimes it's like 2 nitrogens sitting together and so on. And we can also have some complex centers. So it means that we should expect that this type of exciton should be quite common, in fact. So if we look for radiuses of different rare ions and compare it, for example, if they come to zinc oxide, for example, we can expect for some of them at least that strain will be built in. And if we put them in like to strontium sulfide, the differences you can see of radiuses are pretty large. And if you use so-called Pauli scale, which is a strange scale saying about electronegative, the largest value in this scale is 4 for fluor. This is highly electronegative, strongly attractive electrons. Then we see that the electronegative for different rare ions are pretty different, and they differ also if compared to zinc or strontium. So we can expect that both effects in some way may lead to bonding of exciton. Now, okay, so we conclude, okay, it's this idea that this can be this extoning mechanism, maybe it's not so stupid, they may exist. So that's okay. So in this review with Markov scala, we propose several scenarios what may happen if such carriers get trapped, and we discuss two cases. One is called charge transfer state, that one of the carriers is really deeply trapped on like D or F shells, and second by Coulombic and so on, or something which is a full analog of this exciton. And they said this opens the chances the mechanism can report. But okay, if they are common, so why we do not see them? And why, if I look through literature, the number of cases suggesting that such states are existing are really very limited. Actually, one of the first works suggesting that such states exist were done for copper in zinc sulfide using optically detected magnetic resonance, and that I proposed many years ago when I was postdoc in Hull University and using for the first time my carrier optically detected resonance. And we see something which it was indicated that we see some kind of a excitonic relative system. Why they are so difficult to observe? And one more coming to this picture for satellites. And even in a case that we have materials like, say, some 3,5 materials, such centers were observing gallium nitride, gallium arsenide, gallium phosphide, zinc selenide, so quite long range of materials. Then the band gap energy of accidents was pretty large, but you see that still, even when a small portion of energy is transferred from one S to S and so on, these lines were surprisingly strong. Now, once we go to rare science and we have very rich structure of energy lines, this energy transfer should be very efficient. And that we expected that will explain why you can pump so efficiently energy for intracell excitation. And the models should be also considered for some of the transition metals. I already mentioned that we observed something like this in an experiment of optically detecting magnetic results for copper. In rare science, in most of cases, the observations are indirect, but still, very likely, this can be one of maybe major mechanisms expected that we can so efficiently excite rare science. If we go to transition metal ions, I think this hybridization metal I introduced in very intuitive, explain most of the properties I mentioned, so that's okay. Still giving the same value for spin and so on, like we see in electron spin resonance, and this is quite interesting. Whereas if we look for a way we excite them, probably we should consider chances for this new excitation mechanism, and probably especially in case of rare science where we have strictly FF transition, quite difficult energy pumping, they find that we can pump energy from host to these areas can be quite important and can be reason why they finally can be used for some practical devices, not only due to DF emission, but also FD excitation, but also the way we just pump the host. And think, okay, I promised to speak 45 minutes, sorry, it's 50, but it's close. So that is probably my last transparency. Okay.